Hello, everybody. I'd first like to say thank you for coming to this session, and I hope that everybody's having fun at PyData so far and learning a lot of interesting things. I hope that today, people have hopefully learned something new from my session. So my session today is going to have quite a operations research type flavor to it. I'll go into that in a little bit more detail in a few slides' time. But yeah, it's mostly around what we call linear programming, which is one of the oldest, most well-studied techniques for solving optimization problems in businesses and in even academic settings too. So my sessions are going to be focused around that and some of the tools that I've used in the past few years to solve these problems. So before we move on, I'll just give you a little bit of the background to myself and hopefully give you a little bit of motivation as to why I want to deliver this session today and what I want everybody to be able to get out of it. So I work for Tesco, who are a large supermarket chain, primarily based in the United Kingdom. And we have a huge number of stores and part of running our business is being able to run things optimally, and being able to solve optimization problems very quickly is really key to most big businesses, really. And yeah, our data science team has grown over the past few years, and we cover things from all sides of the business, from the workforce in our business to actually more customer facing things. But we also have part of our business as well is really focused on things like transport and fulfillment, which is where really you need to start making optimal decisions to be able to make the business run as efficiently as possible. For this reason, we actually have an embedded operations research team here at Tesco, but I'm not one of the expert members of that team as such, but I have gained an interest in the techniques and tools they use over the past few years. So yeah, just to give you a little bit of a rundown of my own background before we go into the rest of the presentation. So yeah, so I've just mentioned I'm a senior data scientist at Tesco, but my formal background is in astrophysics, as has already been mentioned earlier. So the key thing here is that I don't really have a formal training in operations research. Everything I've learned has been from my own self-study and my own, studying things and trying to solve things myself in the past couple of years. So up until 2 years ago, I didn't even know what linear programming was, or or how to solve one of these things and where they would be applicable. But my interest really started when, at my previous employer, there was a need that was coming in for us to be able to solve optimization problems in our business, particularly around things like workforce, so getting the right number of staff members in to cover the jobs we needed to do and things like this. And at my old job, we didn't really have a formal operations research team there at that time. So a lot of the optimization work was falling on the data science team, who was already in that business. And yeah, it was at that point that I decided to start learning about different optimization techniques and how to solve mathematical optimization problems. It's really there where my own interest really sparked and where I really started to learn about interesting things. And one of the things I did learn about was something called linear programming. So my main aim for today's session really is that for me, I think being able to solve optimization problems is a really interesting tool for a data scientist to have outside of the typical things you see in things like machine learning and classification and things like this, these more sort of typical problems. But, you know, a lot of problems in particular since I've been at Tesco actually come with a prediction and an optimization element to them. And being able to solve the optimization optimization part, as well as just being able to make good predictions, really potentially can make you as a data scientist a really valuable member of a team, and can make you, yeah, just expand the variety of problems that you can actually solve using data. So before I go into the main technical part of today's talk, I would just like to say is that, because I'm not somebody with a lot of formal training in this, I've aimed this session very much at people like me a couple of years ago. It's for people who've never really seen a optimization problem before, or certainly haven't seen it very much, and certainly people who've never seen a linear program. So for this reason, the session's been put together so that you only really need 3 things to really be able to get the most out of this session. Firstly, you need just to be able to use Python and Jupyter Notebooks in particular, which is my own preferred tools for solving these problems, in particular Python. Secondly, to be able to install Ortools, which can be installed via pip on a local machine. And finally, just to be able to see some examples that I've got in this Ortools tutorial, which I've put on GitHub for today. So hopefully everyone can have access to them. And again, I'm trying to make this session as flexible as possible. So the way I'm going to structure it is, it will mostly be me talking and then going through some examples in some notebooks. But if people think that they already know a lot of the concepts here and they want to start doing more complex things, there's a notebook with some problems in which are slightly more, where there's particularly quite a complex one at the end, which so if you feel like you want to go ahead and do that, you can if you want, or if you're very new to this and you don't think you're quite comfortable to be able to solve these yet, you can also just watch me go through a notebook and solve problems as well. So it's totally up to you how you want to do this, how far ahead you want to get in terms of the material I'm talking about. But again, anybody who doesn't have
his name at the bottom, because it was Claire Selleck and you crossed it out to be Morgan. That's really cute. I forgot that even existed.
What was that? Sorry.
I'm sorry, Stephen. Are you asking a question? Or... Oh, he's on mute now.
Sorry. Yeah. Yeah, so really, just to conclude this slide, really, there's 3 things I want people to get out of today's session. Firstly, I want people to be able to understand what a linear program or a mixed integer linear program is, and potentially in their own work, be able to identify when one of these problems might happen. And when these solutions I'm talking about today might be applicable. The second part I want people to do is be able to solve one of these problems on paper. So this is a mathematical programming, really. So be able to formulate one of these on paper. And finally, see some of the tools that I've gained some experience in to solve these problems actually in machine code and get a solution out. So therefore, complete the whole end-to-end cycle of identifying a linear program, being able to write it out, and then being able to solve it. So that's the end of the main introductory part. But now I'm going to go into the first real technical part of the talk, which is a little bit of background into linear programming and what linear programming is. And also what operations research is as well, I guess, is on a more broader scale. So in optimization, what we're typically concerned about are often things called combinatorial optimization problems. So these are problems where there's a set of different X values, or they can be labeled any value you want, really, but to find what the optimal set of these different X values is in from a set of feasible solutions. Now, these are very well studied, and the biggest problem with them, in a sense, is that as soon as you start including several variables and lots of different options that these variables can take in terms of values. These problems, basically, they grow exponentially, and they can take a huge amount of time to solve and look through all of the possible options to find the optimal solution. So very, very quickly, actually, only with a few variables, really, these problems become too difficult to solve quickly if you want to go through every possible solution and find the one that is the best. So linear programs are a similar flavor to this, but the difference is they're not concerned with problems that are found within a set of values. So it's not like examples where x is in 0, 1, 2, 3, 4 or something like this. Instead, this is concerned with finding the optimal solution to the best value of x given a continuous range that it can possibly take. But the key thing here is that both of these types of problems can take a huge amount of time to solve. But actually, what's quite interesting about these optimization problems is that they are really well studied, and actually solutions to these problems, in particular one I'm going to talk about today is what's called the simplex algorithm, were developed actually quite a long time ago compared to most advances in data science. So these were developed in actually the first sort of working algorithm to solve these kind of problems, these linear programs, was actually developed in the 1940s by this guy here called George Dantzig. And he was basically trying to solve a problem about staffing, actually quite similar to the one in my previous job, where trying to work out what the optimum number of people to have in different roles would be. But these optimization problems have a really interesting history because the algorithms for solving these things have been written down for quite a while, again, back to the 1940s, really. But it's only sort of the past 10, 20 years or so that we've started to have the computational power to actually solve them really efficiently. So even though the mathematical formulations are quite old, the computational power to actually get good solutions quickly, which hopefully I'll be talking about today, and we'll give you some examples today, now is actually the time where we're really starting to get good solutions to a lot of big, interesting business problems. So before I move on, I just want to introduce what a linear program is. And the reason I am going to introduce it is that they have a very, very specific form to them. So a linear program is typically concerned with finding the values of different x values, effectively, in these continuous sets that I mentioned earlier. So in this case, it could be x1, x2, x3, all the way to xn. The next thing is you are trying to find a optimal objective function. So that's the second line here. So we've got this find x1, x2 all the way to xn that maximizes an objective function that is c1 times x1 plus c2 times x2 all the way to cn times xn. So the key thing here is that these objective functions have to be linear for you to have a linear program, hence the name. These C values here are constants, effectively, they don't change. And then the next thing that defines a linear program is you then have a set of constraints, which are actually quite similar to that linear objective function, in that they're constants multiplied by the x values, and then you add them all up, and then you're usually subject to some kind of constraint. This could be a capacity constraint of some kind, usually, or they can also come across in quite a few different ways, really. These can be you need to make more than this number of units, or you're limited to creating this many units, or something similar to this. But again, the key thing to point out here is that everything here is linear. So all of these, both the objective function and every constraint we have has to be linear. If not, then we can't use linear programming to solve these problems. And that you have to use something slightly more complicated. But for today's session, we're going to be focusing very much on programs that are very similar to, or that are set up in this exact way. Now, because one thing to point out here is that these are very, very specific cases here that we're talking about. They have to be set up in this exact way. And as I've just mentioned, anything that differs from this, if you had a quadratic expression or something like this, would mean that we can't use linear programming. So if we've got a very explicit problem like this that has to be formulated in a very what's the right word? A very exact way like this. One of the things that I like to do and that I've been told to do is to try and formulate all these problems in a similar way and go through a 6 or 7 step process to solving these problems. So if you are in a business, for example, and you get given a problem that potentially might fit this linear programming style, then the first thing that that I've always been told to do is to just write it down yourself. So describe the rules, which are the constraints, and the objective function verbally. So the reason we do this is that it can help us to understand whether make sure that we've got a linear program and there's not any non-linearities. And secondly, it can help us to just really get to grips with the problem and see what the different parts of the problem are, and really understand it before we actually just start writing down any maths. The next thing we should do is then describe the basic entities of the problem as sets. So I'm going to go through an example in the next couple of slides that will hopefully add a bit of detail to what these things are and give people an example of what we're talking about. But entities are usually, effectively, they're just sort of parts of the problem, really. They could be different products that your factory manufactures. They could be different days of the week. They can be things like this, effectively. The next thing is to describe any related parameters of the problem as sets using the entities we have before. So this is effectively defining these constants, these C values on the right-hand side of the screen and these A values. The next thing is then actually only after you've done those 3 things is you start to actually write the mathematical formulation for the problem that you're going to solve. So the first thing we do is we define the decision variables, and these are your X variables. So a decision variable is so named because it's a variable which can take multiple values, and we're making a decision over which one of them, what value X should take in order to have the most optimal value. Then we write down the objective function using everything we've just seen, these constants that we've already described, these parameters, and also the decision variables, before finally moving on to the constraints of the problem. So steps 4, 5, and 6 is where we go through and do those 3 lines, the find part, the maximizes part, and the subject to part of the linear program on the right-hand side of the screen. And then the reason why it's sometimes a 7-step process is sometimes you have to iterate this, sometimes there's something you missed in the problem. So just iterate until you feel you're happy that you've covered everything that needs to be covered and that you've built your program up. So that's all kind of abstract at the moment, but I've put together an example that hopefully should illustrate some of the points I've just talked about here. And I chose this example mostly because it's, first of all, it's only in 2 dimensions, which is really helpful because that means we can plot it up on a graph and see what the results might look like. And secondly, it's seems to be somewhat physically motivated, albeit it's very, very simplified. So I'm just going to read through the problem statement now. So we've got a crisp company makes two products. There's a premium product and the other one is a standard product. And they supply these to a supermarket. It takes 2 hours factory time to make one of the premium products. And it takes only 1.5 hours to make one of the standard ones. But the profit you get from each of them is different. You get £200 profit from the premium and £125 from the standard product. So the factory is open 40 hours per week, and we have a client who already has a weekly order of 10 standard units that we need to fulfill. The rest of the factory time is free to be used how we see fit. So the question is, how many boxes of each type should we make each week? So a lot of people probably can already hopefully see what the solution to this might be, but we're going to go through it mathematically and demonstrate exactly what's happening in linear programming by doing that. So let's go through this 6-stage process. The first one I'm going to do is just describe the constraints and the objectives that we have. So the first one is that the total production time must not exceed 40 hours. We must produce 10 units of the standard product per week. And the objective is simply to just maximize profits. In this case, it's a very simple objective function. So now I'm going to talk about these entities. And in this case, it's quite a simple one. The entities we have are effectively the two different types of product. So I'll label them as S and P for standard or premium. Then we use those entities to define some parameters of the problem, which are these constants that stay the same. So we have, effectively, we're going to have 4 parameters in this problem. We're going to have 2 for the amount of time it takes to make one box of these crisps, and then there's going to be 2 for the profit margins. So I'm going to label them as T and as P, so we can keep track of those. And I'm going to use subscripts in this case so that we can know which of the products they refer to. So we're using these entities to create these parameters. You then define your decision variables, which in this case, again, it's relatively simple. It's just how much of each item should I be making. Now, the objective function is relatively simple again here. We want to maximize the profit. So that's P is the profit margin per unit that we make, and Y is the amount of units that we make. And the key thing here is that we can immediately see that the objective function is linear. So what we can see here is that what we've got is these constant P values multiplied by these decision variables. There's no nonlinearities here, which tells us that linear programming can be applied to this problem. And finally, let's talk about the constraints. So we have this pre-existing customer order that we've already discussed, and that one that means that we have to make at least 10 of the standard unit. We can't make any negative quantities because that's completely infeasible in real life. So that means that the other products all have to be greater than or equal to 0. And then the final thing is we have a production limit, which again, we can see it's very similar to the objective function, but we can see that it's also linear. It's the time to make each product multiplied by the amount of products that we make. And again, that's got to be capped at 40 because that's the number of hours that our factory is open for. So what we can see here is we have a linear program. Everything is linear, and we can put this into a solver and get the optimal solution out. But before we do that, I'm just going to briefly mention that what this solution looks like on paper. So what we can do is we can actually draw this up because we've only got 2 dimensions and it's a very simple problem. So what we have is we have this vertical line here, which is at 10, which basically tells us that we can't make any less than the 10 units that we've been asked to make the standard product. The blue line that's diagonal is effectively constraining our factory production limit. And the red lines show lines of constant objective value. So in the bottom left, we have £1,000, then it's £2,000, £3,000, £4,000. And just by plotting this up on paper, we can see that the optimal objective value is going to be right in the corner here. It's going to be to make the 10 standard units and spend the rest of the time making the premium product, which actually a lot of people probably may have seen when we did the problem statement. Makes a lot of sense because the profit per unit time of making those products is much greater in that case. So it makes sense to spend the rest of the time making the product as the most profit per unit time. So our optimal objective value is right in the corner. Now, this was a simple problem, but this is something that's really, really key in linear programming, is that even though this is a simple problem, no matter how complex your problem gets, the optimal solution value is mathematically proven to always be at one of the vertices of your search space. So this is how the simplex algorithm does its work effectively, is it's not concerned with this blue shaded region. No matter how complicated your problem gets, what it will do is it will search through the vertices of your feasible region and find the optimal vertex, and that is proven to be the optimal value of the whole problem. So that is why the simplex algorithm is so fast and why it is just so widely used. And there are variations of it and improvements that have been made to it, but this is really the key to linear programming, is if you have all of your constraints and your objective are all linear, no matter how many of them there are, then the feasible solution is always at a vertex of the search space. So that is how the simplex algorithm works in a nutshell. So what we've seen so far is we've seen a linear program and we've written it down on paper. So now let's talk a little bit about how we might, as data scientists, actually find a solution to this problem. Because it's okay being able to write it out on paper, but if we had a more complex one which we couldn't actually draw it out, how would we actually find a solution? So I'm going to go through some of the popular tools that can be used for linear programming in Python. So the way this usually works is there's usually a wrapper, effectively, which are these top 3 modules I mentioned here. So some common ones include Pyomo, Pulp, and Ortools. So I've never developed any of these tools. So if anybody prefers any over the other, I don't mind. But Ortools is one that I tend to use just because I like the syntax of it. I think the syntax is quite Pythonic for me. And also it seems to be very well maintained and have good documentation. Now, it's a tool that's developed by Google, but it is an open source tool that you can use to solve problems. But what these wrappers are usually doing is they are interfacing to a back-end solver, which is usually developed by somebody else. And there are quite a few of them out there. Some common ones you may see if you do some Googling of common tools in Python to solve these problems are listed here. Now, I've highlighted CBC because this is just one that I've used quite a lot in the past, and it seems to give me good results and solve problems quite quickly. But there are others called things like GLPK, and the last 2 on this list here are called Gurobi and Cplex, which actually are very, very fast. But the problem with them is that these are commercially licensed products. So one of the things with linear programming and these optimization problems that often people find is that because it's a much older field of study than a lot of machine learning, there's not so much of an open source community, and the best solvers are actually paid for. But from my own experience, I can say that I've been able to solve a lot of problems at Tesco using a set of open source solvers, including CBC that I've highlighted here. So yes, the best solvers are commercially licensed, but there are free solvers out there, and they are actually very good, and they can still find solutions to problems very, very quickly. But before we move on to actually writing some code, which I'm going to do in a few moments' time, I've just put on the right-hand side here the typical syntax you'll see with Ortools. As you can see, I quite like the syntax. It's very, very simple. And everything you need really is on the right-hand side of the screen. You can set up a solver very quickly, and you can set up variables using these solver.numVar and solver.intVar and set lower bounds and upper bounds accordingly. And then the objective, again, is really simple to write out. You just write either solver.maximise or solver.minimise. And yeah, finally, adding linear constraints is just done using the solver.add functionality. But that's sort of the end of the first sort of technical introduction part of this. And if there are any questions, is probably the first moment we have to talk about them. But if not, I will move on to actually writing some code will be the next part of this tutorial.
We do have some questions, Russ.
Yeah.
So my question is, can you give, or is it possible to give a general big O estimate of the complexity of, let's say, a combinatorial problem in terms of the number of constraints and number of variables? For example, if I want to get a rough estimate of, okay, I know it takes a certain time to solve my problem with 2 categories of crisps, how would it be with 4 categories?
Yeah, so it is possible to do that actually, but it depends on just the complexity of the problem, but or effectively how many categories of things you have. But typically these things scale exponentially, particularly in the combinatorial case, because each variable you add in, what you're going to do is you're going to basically have one extra decision to make, which can have multiple possible values. So if I introduce a new category and it has 2 items to it, then that means that effectively you've doubled your possible search space. So then each time you introduce one, it effectively works like that. But yeah, it really depends on the possible values that you can have, I think. So yeah, sorry, I didn't really answer that particularly well, but generally, yes, increasing the number of variables is just means that for every possible value of that variable, you increase the problem size by that amount, effectively.
Thank you. Thank you very much.
Apologies for dropping off. I guess my internet connection was unstable. Anyway, we have another question, and this is by Deepak. He asks, how do you check if your objective should be linear beforehand?
So this is this is the art of linear programming. Is usually what you have to, this is, if I go back actually to this slide, this is why we start by typically describing the rules and the constraints of the objective function verbally. So what will typically happen is you'll be able to write out your problem and say these are the entities and these are the parameters that are involved. And it's actually by going through this 6-stage process that you find out whether there are any non-linearities or not. And it's at that point that you decide whether I should proceed with linear programming or use something else. So yeah, it's purely in the process of taking the problem on paper to the mathematics that you work it out. So you can't really tell that at the very start if it's a huge complex problem. And I've certainly been in situations where I've worked out after a few hours or so that it isn't linear for whatever reason, but it's the process of turning the paper stuff into the maths that you work that information out.
I hope that answers the question. Yeah, he says thank you. So we do not have any other questions at the moment. So we can proceed.
Cool. So I guess now is the time for me to start writing some code. So again, the GitHub link that I had at the start, actually I could put it in the chat, couldn't I? If people want to download the project,
I put the GitHub link in the chat.
Oh, perfect. Thank you very much. Yeah, it effectively is a going to be a folder where there's going to be some problems and some lecture problems. I'm going to be mostly talking through the lecture problems today, but there's also a much more open problem in the problems notebook as well. So let's open a notebook and let's start working through one of these linear programs. And hopefully here this will hopefully improve people's understandings a little bit, because we're going to kind of reiterate everything we've just gone through. And also hopefully people will see how I tend to structure my code to make this as easy to follow as possible. So the first thing we have to do is we have to import our solver, and to use the CBC backend to find a solution, we have to set up the problem like this. So we just give the problem a name just so we can keep track of it, and then also set the problem type as CBC mixed integer programming, and that will mean that we can interface the CBC backend. So the next thing we have to do is define these entities, which, for those who remember from the lecture slides, I had two of them. They were S for standard product and P for premium. The parameters, so the way I typically write these out is I use dictionaries. So the reason I use dictionaries is that they can be indexed by name. So this means that we can index parameters by for the relevant entities. So we have for standard, the factory build time was, check my notes, 1.5 hours, and for premium, it was 2 hours. The profit contribution for standard was 125, and for premium, it was £200 for every we built, and the total time we have in the factory to make all this is 40 hours. So the reason I set these up as dictionaries is that I can very easily go, well, what's the build time for the standard item, by just doing TI and then just using S as the just using S to index it. The next thing we have to do is set up these variables, which for the standard product, it was 10 because we've got that low limit that we need to make 10. And for the upper bound, it is infinite. And also make sure you name your variables as well, which is important, and give them names that make sense. So I'll just call that one YS because that's exactly what it's indexing. And then exactly the same for the premium product, just the difference is the lower bound this time is 0. We're not forced to make any of these products. And then we have name equals YP. So the next thing we have to do is set the objective value. And the way we do this is I'll show you now with the syntax we use is we just effectively use an inequality. Sorry, not an inequality, that's for the constraints. But what we just do is we use something called solver.sum. So if we remember, it was the profit contribution for each product multiplied by the amount of product we make for each product for I in I. So there we have an objective function, and it's as simple as that to set up with Ortools, which again, I quite like the syntax. It's very easy to access. What we've got here is for each I value, we're just multiplying the profit contribution multiplied by the amount that we've made. Then the final thing we have to do is we have to add this capacity constraint, which was, again, we'll use the solver.sum function to do this. So we have tii multiplied by yi I less than or equal to t. So that should be the problem set up, and all we need to solve this, albeit very simple, linear program. So again, just to reiterate some of the things, I'm using dictionaries just so that it helps me index things in the future. And then I'm using these solver.sum functions to sum over all of the entities in the problem. Oh, that's a... Okay, so let's reset that. So then you run the solver, which is as simple as using solver.solve. And what you typically get back, hopefully, is a value of 0. This means the optimal objective value was found. But if you get other numbers back, they can mean different things. Some of them mean that the problem you've set up is infeasible. There's actually no feasible solution, which has a different numeric value. You can look those up on the Ortools website. And there's also things like unbounded as well. So if we hadn't set a factory production limit here, for example, then we'd just make an infinite amount of items and make infinite profit. But hopefully what we should see is what we saw on the slide, which was that the optimal solution here, we're making the 10 of the standard product, and then we're making 12.5 units. So we're using the rest of the factory time to make the premium product, which is exactly what we saw when we solved this solution on paper. So that is hopefully potentially a lot of people's first time they've seen a linear program solved in Python before. And yeah, that's typically the process I go around doing. But the key thing to note is that I've got the entities, the parameters, the decision variables, the objective values, and the constraints, very similar to what we have on paper, just converted into Python code. So that is our first linear program solved. And I will now start presenting my slides again. Slideshow. So what we've just seen is, sorry, I'm just a couple of slides behind. So what we've just seen is that we can get this optimal objective value from this problem very easily using Python code. So now I'm going to move on to something slightly more complex, and potentially in a few slides' time we'll see something potentially much more interesting, which is mixed integer linear programming. So this concerns cases where we no longer have these continuous variables. So what we've got here is we've got the exact same problem before, but let's add an extra constraint into the mix here. Let's say the supermarket that's buying our boxes of crisps aren't concerned if we have a half full box. They will only buy the product off us if there is a full box that's been made. So what this means is that we have what's called an integer programming problem. It's because the feasible solutions here don't include these half boxes of crisps or any fractional box really. So what we can see on the slides is that these are shown by the black points here. Now this actually makes problems much more interesting, and also means that that linear programming isn't as applicable as it was before. Because what we can see on this slide here is that the optimal solution for the linear programming problem was very easy to find. It was just a corner of the search space. But the optimal solution here, it's a bit difficult to tell just from this slide whether it's the one that's the very top left, that's just below the optimal linear solution, or it could be one of these ones that's closer along the edge as well, might actually give you a better objective value. Now this might seem quite subtle, but this is an important point, that this conversion from linear continuous values to integer values, it's fairly trivial to write on paper, but actually it means that the solver actually has to work much, much harder in the back end to solve this kind of problem. And the reason this is the case is that rather than using one of these simplex algorithms I mentioned earlier, the solver, what it has to do is it actually has to branch the search space into lots of different sub-branches effectively. I'm not going to go into a huge amount of detail here, but the key to remember is when you start introducing integers into your decision variables, it means that the problem might take much, much longer to solve just because the solver just has to work so much harder and do much more clever things to actually find a solution. But the good news for us is that as data scientists, when we write the code, it's a fairly trivial change to make, which I'm going to show now in the notebook again, that it's literally a case of changing a couple of lines in your code, and you'll find the optimal decision variables for these integer problems. So I'm going to do that now. And what you'll hopefully see is that yes, the solver potentially will be working much harder in the back end with a problem like this, but we can write code very cleanly that will solve these in a very similar way, certainly on the front end when looking at the code. So what I'm going to do now is I'm going to make a small change to the previous linear program and find the optimal value of this problem, and I'm going to show you guys how you can do it. So let's open my notebook again. PowerPoint seems to have taken over my entire screen. Let's quit that. Okay, so if my notebook's now being shared.
Yeah, we can see it.
Perfect. So because we've got quite a short, session today, I'm going to just copy the solution we had before, but show you how we can make this into a integer problem, which is, as you can see, as simple as doing this. So before we had these numvars, now we're just going to have these intvars, and we're hopefully going to see something interesting about the solution as well when we do this. So now let's set up the solver, let's run through it, let's get a solution, and let's see what the optimum value is. So this is something that's very, very important in integer programming. So before, the optimal solution was to make 10 of the standard product and 12.5 of the premium product. Whereas here, the optimal solution is to make 12 of the standard product and 11 of the premium product. And this highlights something important, which when you read in the literature actually is quite common, and it's why integer programming is kind of important, is that the optimum solution to an integer programming problem isn't necessarily going to be the vertex that's closest to the corner. Because if that was the case, what we'd have here is we'd be making 10 of the standard product again and just 12 of the premium products. But in this case, that doesn't maximize the objective value. It's better to sacrifice some of the, or at least one of the premium product values, because you can then fit in a couple more standard products that you can make. So that's basically it really on this side. This is the most simple use of integer programming, is when you've got numeric variables that are forced to take integer values. So that is the end of that. I think now is a good time to take a couple more questions if there's any coming in.
Yeah, we have 3 questions.
Yep.
So 2 of them are by Tariq. So first question is like, can we pass options to limit the solving time in case of very difficult MILP programs? And does
Yes.
it work well and returns the best valid solution so far?
Yes, exactly. This is a really important point that I actually didn't have in my slides today, but certainly what often happens is you do get such a huge problem that getting the optimal value isn't often the best thing you want to do, just because it'll take so long. And there is syntax, which I haven't used in quite a while actually, but it's usually typically syntax that you use in the backend solver. So you have to pass arguments to Ortools, and what it does is exactly as was mentioned, it'll give you the best solution that you have so far. And yeah, that's when I mentioned earlier that when you run these solvers, you get these numeric values back, that you get a 0, 1, 2, 3. One of the numbers does correspond to feasible solution that's the best we've found so far, but isn't the guaranteed optimal.
Thank you. And the next question is, does Ortools support a warm start? And that is to say, like passing an initial guess to the solver to speed it up somewhat?
I'm not sure. I've never seen this before. So things like warm starts are typically more associated with heuristic solving methods, which are effectively ways of going through your search space that aren't guaranteed to get you your best solution. I've never seen anything like a Wormstein in a linear programming Ortools before, but I might be wrong. So, but I wouldn't know how to do that because I've not seen anything like that before.
Thank you. And the last question is it possible to index entities over a product of set?
Yeah, you can structure your code however you want. This is just my own preference, how I've done it. But yeah, absolutely, you can do it as just suggested. You can build your sets using whatever syntax you prefer.
All right. Thank you. Thank you for answering these 3. We do not have any others at the moment.
Okay, cool. Well, now I'm going to talk about something much more exciting, hopefully, to me anyway, but I might just be a bit boring, which is where I think mixed integer linear programming really comes into its own. So yeah, so we've just done that previous slide. So now I'm going to talk about a problem statement that's been changed ever so slightly. And this is what the problem statement is that the factory in the previous example decides it can make more profit by manufacturing boxes of what we'll call extra premium crisps. It takes 2.5 hours of factory time to make a box of these, but the profit contribution is much bigger, £275. But there is a problem that to manufacture them, we need to hire an extra machine in our factory that we don't currently have access to. So the question is, should the factory be altering our production strategy? So it's kind of a trade-off here. Is the hiring of this extra machine worthwhile for us? But this should be ringing alarm bells to anybody who wants to build a linear program. And it's in particular, it's to do with the hire of this extra machine. Because what it's doing is, this is somewhere in your problem where you have a non-linearity that linear programming will not be able to solve. Because what you've got is, if you hire this machine, you could make 1 box of extra premium crisps, or you could make 1,000 of them, but that cost is still £500 to the factory. So yeah, this is where we've got something that's much, much more complicated to solve. And this is where, for me, these are the kind of problems that I love solving within mixed integer linear programming. And I've solved quite a few problems like this before. And what I'm going to do is I'm going to walk through the previous examples slides and show you how we can introduce another decision variable that can solve this problem for us, and we can still use at least mixed integer linear programming. So if I walk through the previous problem we had, we describe the constraints and objectives. They're exactly the same as we had before, but the difference we have here is that we've got this extra thing. If we make any extra premium crisp, we'll incur a startup cost of £500, which is, it's a fixed cost no matter how many of these extra premium crisps we make. So let's go through the process. Again, we'll define the entities as sets. The entity is the easiest thing to fix because you just add one extra entity into the problem. The parameters, again, because we had 2, but now we have 3, we just have an extra build time and an extra profit margin. But I'm also introducing something called M, which I'm not going to mention until the very end of this slide, because you'll see what it does in about 2 minutes' time. The decision variables, again, they look very, very similar. The only difference being that we have one extra entity for Y, but we also have something called delta, which is there to keep track of whether or not we need to hire this machine. So delta, what it does is it should be forced to have the value 0 if we don't need to hire the machine, and 1 if we do. So how do we use this delta value? Well, firstly, let's think about the objective function. We've got, again, this very, very similar objective function with the profits, but this time we add something in which is minus 500 times delta. So just to go through exactly why it looks like this, if delta is 0, that means we haven't hired this machine. So 500 times delta in this case is 0. If delta is 1, we have hired the machine. So that means we're imposing a £500 penalty to the objective function only if we hire that machine. But the key question here is, how do we make sure that delta has the right value for the problem at hand? And how do we force it to take the correct value? And this is how we do this. So what I've set up is we've got the exact same constraints as we had before, but this time we have one extra part component to it, which is m times delta is greater than or equal to ye. So let's think about the 2 different scenarios we might have in this problem. The first one is that we don't make any extra premium crisps. So that means ye is 0. In this case, we have this big M value times delta. It's got to be greater than or equal to 0. So that means delta can actually take 0 or 1 in this case. And in the optimal case, it's not going to take the value 1 if that machine's not used, because that's just an imposed cost that wouldn't be doing anything. But now let's consider even the most conservative case where we have ye, we just make 1 box of these extra premium crisps. Even in this case where we make very, very few, what we've got is m times delta has got to be greater than or equal to 1. So this means in this case, delta cannot take the value 0. It is forced to take the value 1. And this is where mixed interlinear programming becomes so powerful, because this is now going beyond the realms of being able to just solve a simple linear problem. We can actually introduce decisions, and these binary decisions in particular are really what makes the problems we can solve with integer programming much, much more interesting. And I'm now going to go through this exact problem in the lecture problems now, and I'm going to see whether or not it's worthwhile hiring this extra machine. So I'm going to go into the notebooks again. So I should now be sharing my screen again, and I should be we should be able to start coding up this slightly more complicated problem. So what we've got is the entities in this case are S, P, and E. the parameters, similar to last time, we just got these extra ones. So we've got S, as before, we've got 1.5, we've got for the premium, it's 2 hours of build time, and then for extra premium, it's 2.5 hours. The profit margins are for S, 125, for P, 200, and for E, we have 275. Factory build time in total, again, 40 hours. And yeah, CE is what I'm going to call the cost of hiring an extra machine if we need it, which I'm going to call, which is £500. So for S, we've got the lower bound of 10 units, which is the same as what we had before. I'm going to set the upper bound as infinite again, and name equals YS. We have lower bound equals 0. Bound equals in, and name equals Y. P. And then again, we're just going to have another decision variable for Y. At this stage, there's nothing more complicated. It just looks exactly the same as it does for premium, which will look like this. Name equals Y. E. Then the final thing I'm going to do is I'm going to introduce this delta variable, which we can see is also an integer. This time it can only take the values 0 or 1. So we can do that using these lower bounds and upper bounds equals 1. And I'm just going to call it delta. The objective function is going to be, let me just check my own notes. But it should be very similar to what we had before, just with this delta component added. So we're going to use the solver.sum part again. Then we have pi times, so that's the profit multiplied by the amount we make, I in I. And then the only difference here is we're going to impose this penalty, which is effectively going to be £500 times delta. And the final thing is we're going to have the same constraints as before for the factory build part of it, which is the 40-hour limit, which you can see is going to be TII multiplied by YII for I in I. That's going to be less than or equal to T. And then the final thing is we've got to really keep track of this delta variable and make sure it has the right value for us. So that is going to be M times delta. If we remember the formulation, it was M times delta is greater than or equal to YIE. So if this Y value is ever so just to reiterate, if this Y value is ever non-zero, then this constraint means that delta has to equal 1. And there we go. We've just set up another linear solver that hopefully will give us a solution. Here we go. And we see that the solution is exactly the same as it was before. So that is telling us that this extra cost of hiring the machine is not worth it. So the answer is no, this factory should not be changing its production strategy based on the inclusion of this, based on the inclusion of this extra premium crisp, where potentially might yield more money, yes, but the factory higher cost of that extra machine isn't worth it. So what we've just gone through is 3 really simple things, and hopefully the last one's the really important one. It's where we've introduced an integer that's really doing an interesting part of the problem, which is modeling a binary decision. And if you've got these binary decisions in your linear programming, then this tells you that mixed integer programming is also might also be applicable to your problem. So that's the end of the sort of lecture slides part of today's presentation. So I guess now would probably be a good time to take more questions if any are forthcoming.
I don't see any questions on the
Perfect.
chat right now, but
Okay.
if anyone wants to, please bring your questions.
Yeah, I guess we could just carry on with the very last part I'm going to go through with the last 10 minutes, and then at the end have any questions as well. So yeah, what I'm going to talk a little bit about now is the repo that I put together, which should be of interest to people here who found this presentation interesting, hopefully. So the repo also has something called problems in it, and what I've got in here is I've got a problem about the location of facilities for a company. So this is being designed in such a way, this notebook, where it gives people a chance to model a potentially slightly more complicated problem using integer programming. I'm not going to actually type through the code now because we don't really have the time, but I might actually show you the solution and highlight a few things to what I do to solve this problem. So the first thing I want to do is I'll talk a little bit about the problem itself that you'll potentially be solving in this notebook if you've got an interest in this kind of work. It is that a large company wishes to move some of its departments out of London. And there are benefits to doing this to the company. They have 5 departments called A, B, C, D, and E, and the possible cities for the relocation are Bristol and Brighton, which actually isn't very helpful because both of those begin with the same 3 letters. So when you're trying to put together your sets of entities, it gets a bit confusing, but I just call the cities by their full names for that reason. And then there's a benefit derived from each relocation. And one of the things I do is in this notebook, it gives you a chance to go through this 6-stage process that I mentioned earlier to firstly describe the rules and the constraints verbally, then to describe the entities, to write them down in your notebook, and then write them down in the Python code style that I prefer, or any style you prefer. The parameters are these benefits matrices. Work out your decision variables and find your objective function and find your solution. Now this one, the first part, the way I've designed this notebook is there's a first part which is relatively simple, and it's basically as long as you have a good grasp of these binary decision variables, which are effectively just keeping track of where each department is located, you'll be able to solve this quite easily. But also, there's a second part of the problem, which is actually the one that's taken from the notebook, where they introduce something called communications costs. And I won't go through the solution because it is on the GitHub repo, but this is something that where you have to introduce what I would call a linear programming or integer programming trick to the problem to solve it. Because what you end up doing is, when I first formulated this problem, is I had a case where there were 2 binary decision variables that were multiplied together, and that's not great because you then have a non-linearity. But what you can do is you can actually use a trick here, which is written in this hint, to effectively force a third decision variable to have the value 1 only in the case where both of the delta variables are 1. And you do that by introducing these 3 constraints. So hopefully if people do have time to go through this or are interested in going through this, they'll see this trick in action, and they'll hopefully get a real understanding of when we can do some really, really interesting things with mixed integer linear programming. But as we only have 15 minutes left, I would suggest that this is a exercise that hopefully people can do in their own time if they have an interest in it. And yeah, at this stage, I think because we only have 15 minutes left, I think I'll probably say my closing remarks about today's session, and then hopefully take any questions if any of those are forthcoming. So let me reopen my slides. And let's go through some closing remarks from me, which hopefully will be very useful to people here. If not, again, I'm not a huge expert in linear programming and mixed integer programming, but this is, my own thoughts from doing this for a couple of years. So the first thing I want to say, which is hopefully going to be a really important thing for people here, is that these mathematical optimization problems are actually super common in businesses. And in particular, any problem that requires us to allocate resources in some way can be modeled in this kind of way. So some classic optimization problems that you might see include things like facilities. So this is an interesting one for us as a supermarket, because it's where should I put my facilities to best serve my customers? So this is a classic problem that's called the facility location problem. Staffing, where should I put members of staff and how many do I need? And this is really where the first problems in linear programming were solved in this space. The third interesting problem to consider is anything to do with resource allocation, which is what we've been talking about today. So if I've got a limited budget, either a factory time budget or a budget to buy things, what should I spend my time doing, or what should I buy in to maximize revenue? And then finally, probably one of the most classic optimization problems is vehicle routing. Where should I send my vans or my cars or anything like this to visit the most places and maximize the most, run my operation most efficiently. Now, the reason I've highlighted these 4 problems is that what I've found over the past few years is that even though problems can come in so many different flavors and have slightly different things that go into them, really a lot of them are covered by these kind of basic problems or are extensions of these basic problems. And there's so many cases in business that I've seen, even in my 1.5 to 2 years just studying these things, where optimization problems are just come up, and you can actually solve them using things like linear programming and mixed integer linear programming. And my own experience in the past year has been that I've been working on a problem that has a prediction element. Then you want to pick an optimal set from your predictions. So yeah, I guess my key point here is that these are really wide-ranging problems, and there's a lot of problems out there that can be solved using the techniques that I've talked about today. And yeah, I think having a knowledge of A, what these problems are, and B, what kind of open source tools you can actually use to solve these without paying anything for commercial solvers can really help your team, and you can potentially start solving really, really interesting problems. The second thing I'd like to say to close is that I've talked through this 6 or 7 stage process. I often am guilty, I have to say, of trying to rush ahead and build linear programs before going through these. But as I've mentioned very early on, these programs are very, very specific in their format, and going through this 6-stage process or 7-stage with the iteration, has helped me vastly in the past year or so. And the more disciplined I've got about that, the better my building of linear programming has got. And by building this program step by step on paper first, you'll really start to get some interesting insights to the problem at hand as well, and really start to understand what's going on in your problem. And then finally, the last thing I want to say is that just keep learning about these problems if they interest you. There are lots of these small tricks and changes you can make in your linear programs and your mixed integer linear programs to make them much more flexible, often much faster as well, just by rechanging something in the formulation and things like this. So, you know, if you think you've got a problem that potentially either can't be solved with linear programming or potentially is going to be very slow, there are often things you can change to make them much faster and much more flexible. And for me, there are so many problems that can be solved in this way if you just try and keep your mind as flexible as possible in terms of trying to introduce these integer decision variables, for example, to make everything much more which basically means that you can just solve so many different things. But yeah, that's all I'm going to say today. And again, please take a look at the notebooks if you want to solve a potentially much more complex linear programming or mixed integer linear programming problem. And the last thing I want to say is that we at Tesco are hiring data scientists at the moment. So if you are interested in potentially working at Tesco and working on some interesting problems, as mentioned at the very start of today's presentation, then yeah, we're hiring for senior positions in typical machine learning problems, but also computer vision, time series forecasting. And we also have a presentation tomorrow by our head of data engineering too, who'll be talking about a much wider scope of the kind of data science we do here at Tesco. But yeah, you can send me a message if you forget what these names are, or yeah, make a note of them. And that's Charlotte Cooper 11 is our recruiter. But you can just send an email to datascience@tesco.com if you think that you found today's presentation interesting, or you potentially want to come and work here. Then yeah, we have positions available. But that is all I'm going to say today, because I feel like I've been talking for quite a while now. And hopefully that leaves us with a few minutes for questions if they come in.
Thank you so much for the amazing session, Ross. We do have some questions, so I'll shoot them away. So first one is by Greg, and I guess this was answered a bit, but I guess this specifically dives into what you do. So the question is, what are the typical real world LP problems that you encounter at your work?
So yeah, so for me, so I can answer that on sort of two stages, I think. Firstly, for the work that Tesco do, it's very much mostly what a lot of big companies do, which is things like optimizing vehicle routing, for example, is probably the biggest area in a company like Tesco, as it would also be in Amazon and any other big business, really. But also for me, I've been working on a predict optimize problem in pricing as well, which I'm not going to go into the details of exactly what goes into the back end of that. But in a pricing problem that I've been looking at, we've we have a prediction element to it, which is to effectively try and predict price elasticity and then do an optimization to decide what the optimal price can be. So yeah, pricing is also an interesting area for these kind of problems.
Thank you for the answer. We have the next question by Courtney, so the question is, maybe you have mentioned this already, but is there a way to extract the marginal values?
What's the marginal? Sorry, can I just repeat that question?
Yeah, so is there a way to extract the marginal values? I'm not sure if. Yeah, that's the question.
Okay.
Connor, if you want, you can unmute yourself and maybe elaborate more on the question.
Yes, so I think also the question relates to the question that was asked after me. So one of the things, can you hear me, by the way?
Yes, yes, I can.
All right, thanks. So the marginal values, I mean, what happens if, for example, a constraint slightly changes, that you go from, like in your example, you had the factory production limit, if it goes to 41, how does that alter your result? That's what I mean with marginal values.
Yes. Yes. So I do actually have an answer to that is yes, you can in a linear program actually. And I haven't ever done any of this, but you can certainly extract this information. And what these are called in linear programming is often called shadow pricing, it's called, I think, which effectively, it tells you how your objective and your solution would change if a constraint was to change slightly. Now, my understanding, having read around this subject very briefly, is that it is very, very limited in scope. So what I mean by this is that, so in the problem we talked about today, it would be, you'd probably be able to do that infinitely because we only really had this one factory production constraint. And if you kept increasing that, everything's going to increase effectively linearly. But what typically happens is in a linear program, you'll have lots and lots of constraints that are all working in a in slightly different directions effectively. And what these marginal values will do is they'll only really tell you what will change if a particular bounding constraint changes slightly. Because the issue you usually face when you build a really complicated linear program is that the constraint that's actually bounding your problem will change, if that makes sense. I don't know if I've explained this very well.
So my question really relates to Ortools. So
yes.
I'm very aware of shadow prices and like the marginal analysis, and that you solve the basically look at the dual of the LP, things like that. So I'm specifically interested in how to extract these values from Ortools.
Okay. The answer is I've never done it. So I can't really give you an answer. My understanding is that you can, because I'm sure I read about it, but again, I wouldn't be able to give you a firm answer to that of how easy it is to do it. So I'm not going to even attempt to give a more complicated answer than that.
Right. Yes. Thank you very much.
Yep, thank you. And this also answers the next question by Moritz, and it was on the same lines. So we have one more question by Corney. So is it, I guess this is a different question. So is it possible to connect with one of the common solvers and examples given, CPLEX and Gurobi?
Yes. So you can change the backend solver quite easily in Ortools, and they do have support for, as far as I could see, there were two that were definitely mentioned, yes, but also Cplex and any other solvers can also be interfaced. It's just a case of changing the argument when you set up the solver.
All right. So this is all of the questions that we have right now. If no one has any other questions, maybe we can end this session. So yeah, thank you so much for this amazing session. I and I guess everyone here enjoyed it. And yeah, thank you so much for being here, and enjoy the rest of your conference.